I hope that everyone can hear me. Christina, please, we should not forget that you pass me the presenter's rights. Thank you very much. Okay, so the Austrian National Weather Service, ZAMG, is presenting today. It's me, Yasmin Markl, and my colleague, Andreas Wirth. And because this weather briefing will be a bit diverse, I would like to give a short overview. So first, I will talk about the synoptic situation in Europe for today. I would like to give a short introduction into the ESSL storms or severe storms forecasting. So we will have a look at the web page there. Then Andreas will talk about the Scandinavian heat wave, and afterwards it will be a short cliffhanger for the satellite interpretation course that is coming up. So let's start. This is the water vapor image from today in the morning at 7 UTC. I would like you to have a look at it and just see if you see any interesting structures, and maybe if you want, you can take a pointer or something and try to find some structures that seems to be a PV potential vorticity anomaly. So get one of the tools and just see if you can find something that might relate to this topic. Yes, we have already something. Thank you. Just go ahead. Yes, very good. Okay. Maybe something more? Any ideas? Okay. Yeah, thanks. Okay, very interesting. Thank you very much. I will delete all annotations, and you have already seen some very interesting structures like this very dark region over here, then some smaller circulations over Europe. We have other structures like here. Let's go one step ahead. Okay, 1 second, I think. Okay, so here I have overlaid the geopotential, and here you can actually see where we have the upper level low pressure system, a huge one approaching at the West European coast, and this other low pressure system or kind of clustered system over the over East Europe, and then we have a high pressure system over Scandinavia. Why do we see this PV anomaly as dark stripes or dark areas? So I have said this is the water vapor image. That means that where it is dark, we see basically drier areas, and those are areas where we have the intrusion of stratospheric air, and so this means that here the tropopause is kind of bended downwards. And where it is bended downwards due to the PV conversation, it is a PV anomaly, and therefore we have also kind of very important effect on convection, because we have this ascending motion ahead of the anomaly and this subsiding motion behind of it. So for example, here in front we already see some very bright areas. So we have here this ascending, and behind we would have the subsiding motion. Okay, so any ideas where we have a jet stream here? Okay, thanks. Yeah, some guesses. Okay, very good, thanks. Yeah, all right. Okay, perfect. Yeah, I will just quickly delete the annotations again and show the next picture where I have overlaid the wind barbs at 300 hectopascal. So these are the areas where we have high wind speed and the jet stream. Okay, so from from this situation, we know actually a lot. So we know where we have the jet stream, so we know where there's probably a lot of shear. We know where we have low pressure and high pressure systems. And in this case, you can already see that we have something like this omega blocking situation that would probably enhance a bit in the next days, and which is also one thing that is responsible for this very hot days, lots of convection, and the situation that we have now. And this omega blocking situation is kind of stable, so that might keep for a bit longer. In terms of convection, let's just jump ahead. I have prepared an animation for you from Wednesday in the morning till the day 11 UTC, and here you can see, okay, I just want to start it. You can see how this water vapor image moves, and also the lightnings that would happen. So this is yesterday. During the day you can see lots of lightning going with this, especially with this small scale cyclones here over like passing Austria and going on to Croatia, where yesterday during the day lightning is quite intense and also lasts until today in the morning, and then today in the morning it increases again. And so playing it once again, and yeah, again lots of lightning going on for today. Okay. Yeah. So would be very interesting to see it then in the evening, the rest of the animation. So I have said that I would like to go with you and have a look at the ESSL database. So first of all, what is it for, and what is convection, and what are the three basic ingredients for convection? I think that's something that should be clear to everybody before we go there. So please select the three components, the three ingredients that you think are most important in general for convection or the development of thunderstorms. Okay, so we have, yeah, some people favoring instability, low-level moisture. We have topography, lifting, shear, of course. Okay, cape. All right. Okay. Yeah, no salt and pepper. Okay, thank you very much. So actually, the most important ingredients is the low-level moisture, then instability, and the lifting mechanism that would actually like initiate the whole thing. And keeping this in mind, I would now like to go with you to the database of ESSL. It's the European Severe Storms Laboratory. I was lucky to go there for the testbed like 3 weeks ago, so it's still rather fresh. I have gained lots of knowledge, especially about convection, of course, and storms forecasting. I can recommend it to everybody. It was really great. And just that you know a few side facts. So the ESSL testbed, it's an annually returning event, and it's made for forecasters, for training. It's evaluating the forecasting tools, and it provides like a platform for international interaction. Yes, so there are 2 seats, one in Wessling in Germany and one in Wiener Neustadt in Austria. So at this point, I want to share my screen because I think that's actually easier to quickly go through this stuff. So 1 second. Okay, I hope you can see my screen now. So this is this Okay, a second. This is this data interface. Here you can see, or here we have different forecasting maps, but also all different kind of data for nowcasting. And here we find the most important things that we need for a storm forecast. So for example, if we quickly go through this map here, this is the geopotential. So I would just have a quick look for the day. So we see this low-level pressure system here over the Atlantic. We have this higher wind speeds here. So we already see at 300 and also at 500 hectopascal that there's quite some wind speed that might also cause some shear at the ground. We have this high pressure system over Scandinavia that causes probably rather not so exciting weather. We can, for example, have a look at the lapse rate and moisture, and we have said before that lapse rate, like the instability and the moisture, are very important ingredients. So we can see here in front of this low pressure system that we have quite high lapse rate, and also here, for example, we have higher moisture content. Also here, north of this the Black Sea, we have higher moisture. We also have quite high lapse rate. So those are probably areas here and in this region where severe convection might take place today. The time step is now 18 UTC, so it's in the evening. We can also, for example, have a look at the shear, 0 to 6 kilometers shear, and and the Cape. So we see Cape practically in more areas, but again, here we have quite high Cape values, and also here in front of this system, but also, for example, here over the Mediterranean, we have very high Cape values. Going back here maybe, and also switching on the radio sounding tool, that is quite helpful. We can, again, for example, look here, we have a rather steep lapse rate. We do have some Cape, and if we go maybe over here, or I think here we should better switch to another model. We do have very high, a very high amount of Cape and only very little thin values. The shear is not that big, but it could be enough for severe convection, for maybe large hail, maybe very intense rain. And also, if we go over here, we have quite some amount of Cape, not so much shear, but still for hail and flash flood or downbursts, this could be like plenty. All right. Also, just have a quick look at the nowcast data. Time is running, so just quickly go through it. I would like to have a look at the RGB EMAs. So this is now, and if we go back, we can see, like in the morning at 8 o'clock, we can see this high pressure system with almost no or just a few clouds, and this low pressure system with a very big area of high level thick clouds. We have this cold ozone-rich polar EMAs here over Scandinavia and Germany, and warm ozone-poor EMAs that is here, like over Spain. Moving a bit forward in time, we see that the thick high-level clouds increase. So this is all the convection that is going on. And if we also switch on the radar reflectivity, and maybe we can also see some lightnings, yes, then we can see what's actually happening, and that there's quite some activity already going on. Okay, thank you very much at this point. I think I should speed up a bit and pass the ball to Andreas.
Yes, thank you.
Please go ahead.
Yasmin. Very impressive tool, and I think you can learn a lot of the combination of the different data we have seen for prediction of thunderstorms. I don't have the ball right now. Can you pass it to me, please? So,
here you go.
Thank you. I will talk about the Scandinavian heat wave that was going on last week, and I had a quick look in some weather synoptic charts, and I will show them to you now. Maybe some of you have also had a look at that weather situation and can add some information to what I'm saying. Yeah, let's start with the early phase of this heat wave. And it was really an extraordinary heat wave, which was breaking some records, long-time records. What we see here is, it's the 15th of July, and what you see here is the geopotential. The temperatures are marked on this chart here. They are not extremely high, but not extremely high at that moment. They will grow to higher levels in the next days. And there is no distinct advection from the south, rather the contrary. We have here northerly stream of the wind, and so the situation does not start with warm air advection from the south. And if we look at the next day, on Monday last week, the 16th July, then we see that in the mid-atmosphere we have a pronounced high pressure area which builds up, and you see here the wind barbs which form a circular wind field. So this is a quite close wind situation. There is no warm air advection from the south. So why do we have so high temperatures? And you see that the temperatures increase here. We have no clouds. We also don't have any convection in the evening. It's clear sunny days, and the temperature here go up to 29 degrees here. Yeah, 28 degrees here in Finland. But also Norway and Sweden is also affected here. You see high temperatures. And in the coming days, this is Thursday, the high pressure system was quite stationary and moved slowly towards the northeast. And the highest temperatures could then be found in this region where the high pressure system is, and lasted for many, many days. Over northern Finland and especially the Kola Peninsula, you see here at noon, 12 UTC, we have 31 or 32 degrees, which is extremely high for these northern latitudes. And so why do we have so high temperatures? Where is the energy coming from? And I think the energy comes from the fact that the sun is shining day and night. We have no clouds. The surface is heated up by the sun. There is no night in this time of the year, so there is constant solar energy coming to the ground and heating up the surface. And in the combination with the high pressure, which inhibits clouds, we come to temperatures which are very high, and it's written here, it's 8 to 12 degrees above normal. So this is a very interesting situation, but this goes mainly in Austria. If we have a heat wave, we have also advection of warm air from the south, but this is not the case here this was not so the case here in Scandinavia. This is a chart I found in the internet. It's the GFS model, and you can see here that the model catches the situation quite well, showing a high temperature anomaly over Scandinavia. Very impressive, and we have a secondary maximum here also over northern Canada. but this is really impressive what we found here. This is the temperature maximum of I think it was Wednesday. Wednesday last week. Let me have a look in the calendar. It was on 18th. No, yeah, on the 19th. Sorry, on Thursday 19th. And you see temperatures which are normal for Central, Southern Europe, but not so much for the Nordic countries. And this is really exceptionally high. And not only Finland was affected, but all Scandinavia was affected by these high temperatures. We have all-time records which have been broken: 14 locations in Norway, 10 locations in Finland, and 3 locations in Sweden. And there was a temperature maximum in Bardufoss, maybe my pronunciation is not correct, which was 33.5 degrees on Wednesday. And this is also was an all-time record and beats the previous one by nearly 2 degrees Celsius. So it's really an exceptional situation last week which happened. And yes, Rob mentions also the drought, which plays an important role, and I'm coming to that. Yeah, we have in one of the next slides, but before we have, I have to mention that the night temperatures were also very high. We had in the northern part of Norway night minimum temperatures of 25.2 degrees, and every night temperature above 20 degrees a tropical night. So we had a series of tropical nights in Scandinavia, which is also exceptional. So now let's come to the drought, which played an important role. And the drought was not only during this last week, but was already starting in early summer. And I have found here a map from Copernicus data showing that large parts of Scandinavia are affected by low soil moisture. And this is a factor which provokes or favors forest fires. This was the case in the last week. Here I found a nice image of forest fire in Scandinavia and all the locations. So it was not on a restricted area, but it was all over Sweden that forest fires started. Yeah. So this was really an exceptional situation for Scandinavia, and temperatures were the same as we have in summer in Central Europe and Southern Europe. So something which does not happen very, very often. So if you have any other ideas or comments why this situation was so extremely dangerous and led to this high temperature, so please comment it in the chat box. Maybe there are some other reasons. Rob wrote that there is no evaporation. Yes, this was seen because there was no clouds, no thunderstorms in the evening, which could have led to decrease a little bit the intensity of the situation. But this was not the case. So it was very dry, and then we had the high pressure, which increased the gravity of the situation. Okay, let me announce at the end a course which will take place at the end of the year, starting in October and lasting until end of November. It will be the Synoptic and Mesoscale analysis course, where you can learn how to interpret satellite images, mainly in terms of conceptual models. So this course is organized by the DWD, by the German Weather Service, together with EUMeTrain. It will be a double structured course. It will have an online phase of about 1 month and a classroom phase. So you can combine those, but you can also say, I just want to follow the online course. You're welcome to to register to this course. The registration is open, so if you are interested in that topic. My last slide just shows you the topics which will be treated during the online part. As I told you, it will be mainly conceptual models. It will deal with all over it will treat with many conceptual models. It's not restricted to a special topic. So we will have frontal situations, subfrontal structures, cold air features, mesoscale features, cold air features, and this time we also included gravity waves, Lee waves as a special topic. Convection will play a role. Low cloudiness, shallow clouds, fog, and stratus. So I think all possible summer and winter situations will be treated in this course, and the main topic is conceptual model and recognize this typical cloud features from satellite imagery. This is the topic. So you're very welcome to join the course if it's something you are interested in, and there will also be a 1-week classroom phase which helps you then applying what you have learned during the online phase. But it's not a need. You can only take part at the online part if you don't have time for the classroom phase. So that's so much from my side, and if you have questions, please ask me or post it in the chat box, and I give back the ball to my colleague Yasmin. Yes.
Yeah, thank you very much.
For the last words. Thanks.
Okay. Thanks. Thanks for giving me the last words. I think we are almost done. Okay. So here we go. Thank you for your attention. So if there is any discussion or any questions, anything, just write it in the text box. You can also raise your hand or give us some signs so we can pass you on the microphone and we can talk a bit longer. A short announcement: the next weather briefing in August is held by the Finnish weather service, the FMI. The specific date is not, I think, not fixed yet, but you will find all the detailed information on the website on EUMeTrain. So just look for it, or you can also subscribe for the weather briefing newsletter. Thank you very much. If there's anything, or Christina, you have something left to say?
I just wanted to say that the next weather briefing is going to be on August 28th. So.
August 28th, perfect. Okay, thank you very much.